Hello everyone, so today we're going to be deriving the expression for the overall thermal resistance for heat transfer across materials in a series and in a parallel. Right now we're about to go over in a series. So firstly we're going to start with our coffee problem. Just to kind of give us a little frame of reference here. As we have temperature 1, temperature 2, temperature 3, temperature 4. Actually, I wrote that out wrong. Sorry. So, we have our coffee, our glass, insulator, and our air. So if we want to remember back to our previous lesson with what a resistance equals for convection, resistance across convection is equal to 1 over the H value times the area. And our resistance value for conduction would be the length times K value, thermal conductivity times the area. So keeping this in mind, we will kind of set all these equal to each other because we're going to assume steady state right now. We'll put absolute values around it so that way we don't have to worry about the flow of energy. And then just for a reminder as well, this is Q convection, this is Q conduction, this is Q conduction, this is Q convection. So, keeping that in mind, our Q values for each of these, as we're going to use the resistances, we'll have for the first one, temperature 1 minus temperature 2, with resistance of coffee. We'll actually clarify that it is a convection one. Put absolute values around this, set them equal to each other. Temperature 2 minus temperature 3. Resistance of conduction of the glass. Again, absolute values. Temperature 3 minus temperature 4. The resistance of conduction over the insulator. And for our last one, temperature 4 minus temperature 5. The resistance of convection of the air. All right, so keeping this in mind, we can kind of set these equal to each other to have the temperatures separated out from these resistances. So our Q coffee and resistance for our Q value. Q value of resistance glass, T2 minus T3, Q value times resistance of the insulator, T3 minus T4, and lastly our Q value of the resistance of the air, T value T4 minus T5. So, with all these in mind, we can sum them together And then we'll have all these summed together. Actually, I'm going to put that Q on the inside. This is actually just equal to T1 minus T5 over T air minus T coffee. So this is our expression for thermal resistance of materials in series. Alright, so now we're going to be doing part 2, as we're now finding the thermal resistance of heat transfer across materials in parallel. So we're going to start with a little bit different problem to try to explain this. Is we're going to have two materials, a thermal conductivity of glass and a thermal conductivity of wood. Now these will have the same length, but they will have different areas. It's a key part to notice, and they're also going to have different thermal conductivities. So temperature 1 and temperature 2. So, to start, we got to remember our electrical circuit similarities and derive this in the same kind of way. So, our resistance, as we remember, of the glass, it's going to be that length that we have down here. Thermal resistance glass and area glass as well. And our thermal resistance wood is again that length, thermal conductivity wood, and the area of the wood as well. So these are the two thermal resistances that we're going to be working with in this problem. So to find our total overall thermal resistance, we're going to use our properties from electrical circuits. And we'll have our wood plus our glass. And then we get to submit these into our problem. So our total our wood, which is equal to length, wood, our thermal conductivity, and our area of the wood, plus 1 over length, glass, area of the glass. Fantastic. So that can be further simplified down. Let's not make this so confusing. So there's our first expression that we can use, which is right here. Now our second expression that we can use relates more back to that Q value. So our total Q value, Q total, will be equal to temperature 1 minus temperature 2, thermal resistance of the wood, thermal resistance of glass, which simplifies down to Q total over delta T, or R total, or just simply so that's how we derive our overall thermal conductivity across a parallel. Thank you very much. Hello everyone. So today we're going to be determining the total resistance, thermal resistances of a typical home. So first we're going to go and draw out our problem as they're all big. Mine right here. And this will be with a window as well. So we have a double pane window with argon in the middle. And then on the outside we're going to have brick. And then we will have drywall and studs. Or insulation, excuse me. Insulation and studs. And then we will have drywall. We'll have temperature of the inside, temperature of the outside. So, we have two different areas that we're going to be focusing on. So first we will attack the drywall side, and then we'll go after the window and argon side as well. So this first side we're going to go over. The first thing that points out to us is the studs and the insulation. So these are resistances in parallel. So this will be solved by, we're not going to dive into the math today, but we'll have resistance insulation plus resistance stud 1 plus the resistance of stud 2. And we will call this R1. So now we have our three resistances in parallel that we have of the brick, the drywall, the outside, or 5, excuse me, with the air from the outside, the brick, our resistance 1, our drywall, and then our inside temperature. So we'll have resistance the outside air through convection plus resistance of conduction of the brick plus resistance of conduction of 1, R1, so we'll just denote that with a 1. Then we'll have a resistance of conduction of the drywall, and plus a resistance of convection of the inside air. And this will give us, we'll just put this, denote this as R2. So we have this side kind of cleared out through our parallel first, and then we added up all these together in series to get our R2 value. And now for our other side, which is a little more complicated with the window, argon, and another window, and the double side window. So there's a lot to unpack on this one. So we'll start from the outside air and going to the inside. So this is all in series, which is nice. So we have our window, our outside air, so you have convection of outside air, plus our R conduction, the window, plus, I want to make sure I'm going off the screen, our R convection of the window 1, I should note that, window 1, can I go over one? Yes, I can. And then we have our R value, convection, window 2. We'll clear that up. And then we have our R value of conduction, window 2. And then finally we have our R value of convection, resistance of the inside air. I want to note this as R3. So now we have both these sides taken care of. That just leaves us with R2 and R3. Terrible. So these are in parallel now, so we can just add these up together as we would in parallel. 1 over R2 is 1 over R3. And that will give us our R total. So that is how you solve a typical home of total resistances with a window and a typical home with studs, drywall, brick, and then a window with argon, with a double pane window with argon in the middle. Thank you very much.